Welcome. This video is going to explore standard heats of formation a little further and also a variation or an extension of Hess's law. So the standard heat of formation is the change in enthalpy accompanying the formation of 1 mole of the compound in its standard state from elements in their standard states. And by the term standard state, we just mean the state a substance would normally be in at standard conditions, which is 1 atmosphere or 273. So just think of standard state as being the normal state. So after Hess proved his idea, scientists realized his idea could be expanded or extended if we knew the energy required to form any compound. So scientists set about trying to come up with these heat of formation values and assign them based on the idea that pure elements have a formation value of 0. So anytime a pure element is involved, the standard heat of formation for elements is considered 0 because we had to have a starting point, and we don't form elements. We haven't gotten good at that, at forming the natural elements that are here. So the reactions and the heats of formation values can be used in Hess's law to, again, help us calculate even more enthalpy values. So let's look at an example of this. So if I look at this reaction, H2S plus 4F2 yields 2HF plus SF6, I can look at the reaction that formed each substance, each reactant, and each product in this. So equation 1, H2 plus S would yield H2S, and you notice I have the state that each is found in under standard conditions, and I've got the heat of formation value. The second equation, there really is no equation because F2 is going to be 0, so I don't need to write an equation for that. The third equation, 1/2 F2 plus 1/2 F2 yields HF, that's my first product. And then S plus 3F2 equals SF6. So now to apply Hess's law, I have to look at each of these 4 equations, really 3 I guess, but we'll call it 4 equations, and see what needs to be done to each. So my first equation, H2S, needs to be on the reactant side rather than the product side, so I'm going to have to flip the first equation. The second equation, which really is an equation, since it's 0, we can just ignore that. And then the third equation, 1/2 F2 plus 1/2 FF2, that needs to be doubled because I need 2HF in my final equation. And then the fourth and final equation is fine. It's going to yield the SF6 that we want. So let's look at what happens when I make those changes. So the first one, I went ahead and flipped it. So that means I also switched the sign to a positive 21. What's now my second equation, I've doubled. So I also doubled the heat of formation value. And the third equation needed no change. So now when I look at my big combined equation here, again, I can cancel out common terms. So H2S, that's fine. H2, that can cancel because it appears on both sides. F2, that's repeated, so I can add it up to get 4F2. And then the S appears on each side, so I can cross it out. So you see I am left with my 2 reactants, H2F plus 4F2, when I add up my F2s. And it's going to yield 2HF plus SF6. So then my enthalpy changes have become positive 21, negative 546, and negative 1220. So my heat of reaction for this final desired equation is going to be negative 1745 kilojoules. But it's actually simpler than that when you have heat of formation values, because if I just looked at my equation here and I plugged in the heat of formation values that I just had from those previous equations, I end up with the same thing. I have 1 H2S for negative 21. I have 4 moles of F2, but 4 times 0 is still 0. I have 2 moles of HF times the negative 273 for negative 546. And I have 1 mole of the SF6 for negative 1220. So I can just summarize much quicker just by using the heat of formation values. I really didn't need the full equations for those. The only thing that's different from when we did it using Hess's law is that the negative 21 had to flip to a positive 21, which makes sense because the equation had to be written in the reverse of the formation, and when you flip an equation, you have to flip it over. So what scientists found is that Hess's law can be extended or adjusted to what they now call the summation equation, which says using standard heats of formation and Hess's law, you can simplify it with the following equation. Your heat of reaction should be equal to the sum of the heat of formation for the products minus the sum of the heat of formation for the reactants, which means you find the heat of formation for each substance involved, whether it's a product or reactant, and you multiply it by the number of moles called for in your balanced reaction, and you should be able to calculate your heat of reaction. My example says using standard enthalpy values, determine delta H for the combustion of methane. You will need to find these standard values on a reference table. Well, before I know which values to look up, I have to have my equation. Remember, my equation should be combining methane, since it's combustion, with O2, and then it's going to yield CO2 and H2O since it's a hydrocarbon. And each of these substances should be in its standard state, or how it exists under standard conditions. So methane is CH4. Its standard state is a gas. O2 is also a gas. H2O has a standard state as a liquid, though, under standard conditions. And CO2 is also a gas. So now if I look up these values, I see that CH4 has a heat of formation of negative 75 kilojoules. Oxygen has a heat of formation of 0, whereas H2O has a heat of formation of negative 286, and CO2's value is negative 394. And so now, if I use my summation equation, I want to take my products minus my reactants, and I forgot to balance my equation, so I'm going to need to balance that first. So CH4, just have one carbon is good. I need a 2 here to balance my hydrogen, which gives me 4 oxygen, so I'll need a 2 here. So now when I take my products, I'm going to have 2 times the negative 286 plus 1 times the negative 394, and you don't need to include the 1 there, but make sure you look at the coefficient. That's my products. And then on my reactant portion, I'm going to subtract the reactants. That's because they're not being formed, they're being decomposed, so the sign needs to flip. I have 1 CH4 at a negative 75, and I have 2 oxygen at 0. And again, you probably don't have to include all that math, but just making sure you realize you have 4 values to plug in. So when I do this, then my negative 286 times 2 plus the negative 394 minus the negative 75 is going to give me a delta H for this reaction under standard conditions of negative 891 kilojoules. So for my try it here, I've got a couple equations for you to use heat of formation values, calculate the heat of reaction for the following. So you're going to need to find a chart to use, and your chemistry textbook, or if you just Google it online, you should be pretty easily able to come up with a chart that will give you these values. So if I look at the first one, 2NO, I have a value of 91.3 kilojoules, and depending upon your reference chart, your values may be off by a few tenths or whatever, not a big deal. Oxygen's going to be 0 since it's an element, and NO2 as a gas is going to be 33.2. So using my summation law, I'm going to take 2 times 33.2 minus 2 times the 91.3, and when I do that, I'm going to get a value of negative 116.2 kilojoules as my heat of reaction. My second one, I have SO3 gas, and that's negative 454.5. I have H2O as a liquid. Make sure you look up the correct value. This is negative 285.8. And then I have H2SO4, which is aqueous, and that's negative 743.1. So let me just scroll up here so I have some room to work. Fortunately, this is a 1-to-1-to-1 equation, so this makes it pretty simple. I have negative 743.1 minus negative 454.5 plus the negative 285.8. So when I go ahead and punch it into my calculator, negative 743.1, and I like to distribute this negative through. So this is really, those are each positives. So plus 454.5 plus 285.8, I'm getting a value of negative 2.8 kilojoules.